Okay. Hey, I'm gonna get started. Is there anyone else from DYN body that you guys are expecting? Okay. Okay, yeah, I'm recording, so I can send it out to anyone who can make it. Can you guys hear me? Okay, by the way, I can wear the lapel mic if not. Okay, cool. All right, we good on Reacts? Okay, so yeah, today I'm going to be going over, I guess, a quick crash course on solids. So typically in the ME degree plan, you'd be taking, I guess, statics and dynamics first. We're kind of skipping over that since a lot of the leads kind of know that. So the idea is that kind of those subjects are covered by the leads, and we'll cover, I guess, any supplemental topics from then on. So yeah, for reference, a lot of people on the team like to use Shigley's. I'm sure all the leads have referenced this at some point. So I can send out a PowerPoint with all the links. We basically pirate everything off LibGen. So yeah. Okay, so yeah, I guess to start out with, so most people, when they join LHR, I guess at some point start designing a part. And a really common, I guess, misconception that we see at the beginning is that we have these tools like FEA. You design your part and you just plug into FEA afterwards, and you basically say, does my part fail or does it not fail? And that seems to be like the general intuitive way that people approach it. So a really common and natural question I guess we get is, why do we need to understand solids? Like if we have the tools that already compute whether the part fails or not, and it tells us how to change the part if it fails, like methods like generative design or things like that, why do we need to actually understand like first principles? So I put together this really rough diagram just to kind of illustrate like how you might design a general part. So we don't need to go into super fine detail on it, but the general idea here is that when you start out designing a part, it's really important to, I guess, check your intuition against whatever the results of your tools are outputting. FEA is great, and if you use it correctly, it can permit you to design extremely complex parts that you wouldn't be able to do by hand in the past. But the issue with that is if you don't actually understand the first principles behind it, you're not going to be able to tell if your FEA results are valid or not. And you'll also have a really difficult time in terms of deciding where to start when designing your part. So when I design, I guess, any general part, the first thing that you do is identify the loading conditions and what kind of constraints that part is subject to. And then after that, if you have a working knowledge of solids, you can do a lot more than what you could do with FEA. So for example, if I have an extremely simple part, you don't even need to go through the process of taking your part, setting up the constraints in FEA, applying the loads, meshing. Like all you really need to do at that point is take one constitutive equation and understand whether your part is going to fail or not. And that's a much faster check than going through all of those steps in FEA, right? Like there's a little more work upfront in terms of understanding solids, but you're able to assess really quickly if a part is going to work for your system or not if you do it like that. So if you have those understanding of first principles, then you basically have the secondary loop where you can check your part against those equations and see if it passes your loading standards. And then only after you kind of do that initial step in characterizing your part with your understanding of solids do you go to FEA to refine it. And for more complicated parts, it's still super useful to have this working knowledge of solids, right? Like if you're designing an upright, for those of you who aren't familiar with it, the piece that essentially houses the hub and connects to the control arms and holds the wheel assembly, that's a relatively complex part, and it's really hard to tell where to start out with if you don't have that understanding of solids. But if you have a general understanding that, hey, there's this moment load that I need to react on the outside of the vehicle, and I need to design it in such a way so that it's extremely strong and stiff in that bending load mode, then you have a much better baseline for starting to design the part than if you had basically just designed, I don't know, a cube and through an FEA. So in my opinion, that's why having this understanding of solids is important. It provides checks, I guess, throughout your design process, and it also allows you to get an intuitive understanding of your system that you won't otherwise be able to if you just solely rely on these tools. So yeah, I'm not suggesting that you understand all the partial differential equations, finite element theory that goes into FEA or anything like that. I'm just saying that having a baseline understanding of solids is really useful. Okay, so in solids, I guess the idea of it is that you normalize your description of how a part is loaded to different parts. So the most common term you'll hear in solids is stress. So why do we talk in terms of stress and not things like forces? Stress is super useful because it essentially normalizes your description of how the part is undergoing a load. So parts fundamentally fail because of, I guess, the loads on atomic level. And those loads are dependent on the pressures that the part sees or the stress, as opposed to just the pure forces. Like if I had two rods of different diameter and I applied the same force to it, you wouldn't expect them to fail in the same way, right? But if you normalize that description to pressure, then that allows you to, I guess, predict the failure of both parts in a consistent manner. So in general, stress is really just a pressure. It's the load on your part over the area at that interface. And the strain describes the displacement of the part. So the displacement, I guess, is a relatively simple formula. And what we refer to the displacement is strain. So strain is more like a percentage change in the displacement of a part, as opposed to, I guess, like an absolute change. So the formula for strain is the length after your part has been loaded minus the unloaded length divided by the unloaded length. So it's really just a relative change in some dimension. So the most fundamental concept in solids is that my stress, kind of my normalized description of the loading the part is undergoing, is related to the strain, which is my kind of normalized description of the displacements. So fundamentally, everything kind of behaves elastically. There's a relationship between how much stress or force per area I put on it compared to the relative displacement. So characterizing that relationship in different types of loading is kind of the name of the game in solids. And there's a whole bunch of different patterns that you see in terms of these loadings, and we kind of bundle them into separate categories. And by looking at stress and strain, that allows us to predict not only the relative, I guess, failure points of parts, but also their stiffnesses and displacements, which is something that you care about a lot in design. So speaking of stiffnesses, the general way that we describe that is something called the modulus of elasticity, or the Young's modulus. So think of this as just a spring constant, but extended to, I guess, a continuous part, or as opposed to a single spring and discrete element. So the Young's modulus is just a stress over strain, so the pressure over the relative displacement. And depending on the part, you can have, relatively large differences in this value. For example, something like steel is extremely stiff, and will have a really high Young's modulus. The force or pressure that you apply to it causes a very small displacement. But something like aluminum will have a much smaller Young's modulus. So the Young's modulus, I guess, is really important in characterizing the stiffness of your parts. So the Young's modulus is an intrinsic property of the part, but it can really affect the stiffness on a bulk level once you design the part. For example, if I have a shaft and I'm trying to characterize the relative, I guess, displacement of it under a load, the higher the Young's modulus or the stiffness, the less it's going to deflect per that load. So it's important to, I guess, understand the relationship between stress, strain, and modulus of elasticity. And those are pretty much, I guess, the three core principles of solids. Okay, so going into a bit more detail, the way that we kind of characterize that, I can't hide my bottom bar, which is really unfortunate. Let's see if I can. I don't know how to hide it, it's whatever. Oh, there we go. Okay, so yeah, we use these plots called stress strain curves to describe these relationships. So if you look at this plot right here, on the bottom axis, you have the strain or the relative displacement, and on the y-axis, you have the stress or the normalized loading. So as we were saying before, there's a fundamental relationship between the amount of load that the part undergoes and the amount of displacement it undergoes. So for this initial part right here, this is what we call the elastic region. So this is where the part behaves basically like you would expect spring to. It's very linear. There's a proportional relationship between the amount of load you see on the part versus the amount of displacement. And after a certain point, you reach this, which is called the elastic limit. So that point is where the part basically starts to behave non-linearly. It's a spring that doesn't have a proportional relationship between the two anymore. So it's like a K value that's not constant. And then shortly after that, you get something called the yield point. So this is typically what we design parts around, right? You want to design your parts such that the stress is under the yield strength. And the yield strength, the physical interpretation is that once you pass that point, your part will no longer elastically return to the original unloaded position. So if you load it past there and you let go, it's going to contract back a bit, but it's not going to go back to where it was originally. And any permanent deformation in your parts is generally a bad thing when you're designing race cars, right? Like you don't want to load your part and then have it come back to somewhere that's, a position that's different than initially. That's not a good idea. So yeah, the part won't necessarily break, but it'll deform permanently, and that's not what you want. So if you keep loading it past that, the super strange thing is that you can have this effect where the stress actually decreases as you displace it more and more. So a lot of the basic testing that you'll see is basically you just have two grippers and it's pulling this part further and further apart. But after you pass a yield strength, you'll get this little dip in the stress. And that's, I guess, kind of corresponding to the fact that it's yielding and failing. And if you keep loading it more and more past that point, eventually you get to U, which is what we call the ultimate failure point. So this is like literally where your part will break and it's completely unusable and it just separates. But again, we typically design for the yield point and not the ultimate failure point because we don't want our parts going back to a position that is different than originally. You'll also see, I guess, some charts reference what's called true stress and engineering stress. So it's not super important to understand, but the distinction here is that the true stress is as you, for example, pull on a metal rod, you'll get a contraction in the middle that changes the effective area of that rod. So there's both, I guess, an increase in loading going on and a change in area going on. So that's the true stress. So that's like physically what's going on. But typically when we test parts, we just say, oh, it has this initial area, and I'm just going to assume that area stays the same as I load it more and more. So that's what's known as the engineering stress. And for most intents and purposes, you'll just be using the engineering stress. But if you ever hear true stress, just understand that it's accounting for that change in area as you load the part. So obviously your pressure is going to be higher than if you had just used the engineering strength. Something you'll also see is, I guess, what they refer to as the 0.2% offset line. And that's on plot right here. So that 0.2% offset line essentially corresponds to, it's like a general rule. Most parts tend to kind of fail after you displace it about 0.2% of the original length. So if you just go up and follow the line parallel to the elastic line, you'll typically hit close to the yield point at that 0.2% offset on the strain. So that's more of a rule of thumb more than anything, but it's basically a way to approximate where you would expect the yield to be for a normal metallic part. Okay, so you can take this a little further, and there are some properties of materials that we care about even beyond stress, strain, and stiffness. So a lot of parts on the car undergo, I guess, unique loading conditions. They might experience shock loads or extremely repeated loads. So there are two values that we kind of care about in terms of dealing with those kind of scenarios: the resilience and the toughness. So if you've taken, I guess, physics 1 or I guess any calculus-based physics, you'll know that you can kind of correspond the amount of energy that a spring contains just by integrating the force times the displacement, right? And the force is given by kx, so you get half kx squared for the energy. It turns out that it's no different when you go to these parts. It's really analogous, right? You have a continuous material and the behavior is a little more non-elastic after you go past the elastic point. But fundamentally, like, it's still some kind of like springy elastic material, and you can predict the amount of load or energy that it can absorb by taking the integral under that curve. So the resilience is, I guess, rigorously defined as that integral that I'm talking about. Rather than using forces, again, we use our normalized descriptions of pressure and relative displacement. But the resilience, I guess, measures how much the part is able to absorb energy per unit volume. So if you just integrate this whole stress strain curve up until the failure point, that kind of tells you the, sorry, let me rephrase that. The resilience is just up until this elastic limit. So it is defined rigorously as the integral up until the elastic limit on the strain. So yeah, you can kind of define that in different ways, but the toughness is also similar, but you're just integrating up until the I guess, the failure point or the yield point. So both of these values are essentially measuring the ability of the part to withstand, I guess, impact loads. So if you want, I guess, a tougher part, you would tend to choose one that not only has, I guess, maybe a higher stress level, but also is maybe like a little more ductile or is able to absorb that impact better, right? If you have a super small displacement or a really high stiffness part, even if the yield strength is super high, the area under the integral can be pretty small. So higher yield strengths don't necessarily always correspond to tougher parts, and that's an important thing to understand. Okay, so there's also a couple unique behavior of parts that you tend to recognize once you deal with certain kinds of materials. So I won't go, I guess, into the whole material science aspect of this and how this works on an atomic level. You get a little exposure to that in materials, but these mechanisms, I guess, are fundamentally on the atomic level. But if you kind of recognize the results on a bulk level, that's pretty much all you need. So one of them is called strain hardening. And the idea is that the material, once you pass the yield point, develops something called dislocations within it. And that essentially changes the amount of energy that you need to deform the material further. So after you stretch it past the yield point, if you look at it on an atomic level, it's actually fundamentally different than originally. So you'll hear this referred to as dislocations in materials. Again, not too important that you understand that now. But this is important because when we make parts, you're essentially yielding the material when you machine it. So if you're not careful heat-wise or how you load the part, you can actually change the material properties of your part as you're machining it. So this phenomenon, again, occurs both in machining and in practical operation, but you can actually change the material properties of the part if you load it in an undesirable way. And strain hardening is kind of that idea. If I apply too much strain to this part and deform it past the yield point, it actually takes more energy to, I guess, load that part for the equivalent amount of strain in the future. And this can also lead to differences in, I guess, ductility and toughness. And you just need to be aware, I guess, of the effects of machining and loading the part past where it's supposed to be. Certain other types of materials are also super interesting where, let's say I pulled on it and I was still under the yield strength. For metals, you would basically expect it to basically hold that tension forever, right? Like if I take a metallic rod and just hold it in tension and I check on it 2 days later, it's still gonna have the same amount of stress in it. But for certain types of materials, most notably plastics, you get this effect called creep. And the idea behind creep is that that tension in the part actually relaxes itself. And if you've ever played with like silly putty or anything like that, you'll know that like when you pull on it, you kind of feel that initial tension in the silly putty. But like as you keep holding it there, eventually it relaxes. So that phenomenon is called creep, and it's also important because if you're loading this part, like you need to be, in a lot of cases, you want to hold that tension, right? The part is supporting some other load that you expect it to be held there in a predictable way. But if you're not careful, creep can cause, I guess, assembly misalignments or, I guess, differences in how your parts react to load. So again, not a huge concern for metals, but for certain things like plastics, that's a phenomenon you need to be aware of. Okay, so yeah, we'll go back to, I guess, the kind of definitions of stress strain I described earlier. And I mentioned that there's certain patterns of loading that you need to expect. So whenever I'm designing a new part, I always look for these patterns initially. So this very basic case is what you would refer to as axial loading. You just have some part and you're applying 2 loads to it on opposite sides, right? This is really like the most basic you can get with any type of loading. But you'd be surprised like how far you can go just, I guess, knowing these like basic patterns and like applying them to your parts. Like for example, the control arms, the suspension control arms on our vehicle, like they're really just loaded in tension and compression because of the unique way they're constrained. So for the most part, you can predict the failure of like a pull rod just with like one equation, which is, pretty crazy. But like, again, these fundamentals go surprisingly far. So the normal stress for an axial loaded part, and normal just refers to, I guess, if you kind of slice that plane that's perpendicular to the load, that's what we're talking about as a normal stress here. So this is just saying that, it's your force over your area of this, this bar. and the relative change in the length is, again, just dependent on your stress over the strain. And the strain in this case is just kind of intrinsically baked into this equation. So the stress is the pressure and the strain is the length over the area times the modulus of elasticity. So you basically are just relating all of these three parameters to each other: stress, strain, and elasticity. So another super common type of loading that you'll see is something called bending loading. So if I were to take my phone and essentially just try to bend it, that's what your bending load is. This is like a really fundamental load on the car as well, and most of our critically loaded parts are actually in bending. So the bending load, I guess, is there's a fundamentally like different description of how we apply force. It's actually not a force, it's a torque or a moment. So the moment, I guess, is applying a net torque about the plane coming out of page. So the z-axis in this case. And that kind of results in a different behavior and loading of the part within the part. So in axial loading, it's super nice and symmetric. You just take a cross section and intuitively, like, you just understand that the pressure is the same in that cross section. In bending load, it's not really the case. You get kind of a unique distribution of loads within the part. So again, when we refer to the normal stress, we're talking about, like, if I were to slice the part and like look against that surface and how much pressure is going at a certain point in that cross section, that's what we refer to as a normal load. So again, if I take my phone and I bend it like this, you basically get two different types of stress. On the top surface, where it's I'm bending it kind of together like this. The top surface, you get a compressive stress, whereas on the bottom, you get a tensile stress. So compressive meaning it's, I guess, pushing together, and tensile, it's pulling apart at the bottom. So you can see that depicted in this image. And the unique thing is that there's this thing called the neutral axis. So for any part that you bend, regardless of the geometry, there's some line on it where there's zero stress. So that kind of makes sense, right? Like, you're transitioning from a tensile stress on the bottom to a compressive stress on the top. And at some point, you have to pass zero to do that. So for this basic form of loading, like, basically all you need to know is that that load is changing from the bottom to the top from tension to compression. And the form of that change depends on the geometric properties of the part, and that's all, not the material properties. Right. So in order to react it, there's basically a whole bunch of tiny forces on the surface of the part at that cross section, and it's solely dependent on the geometry. So the general equation is that the stress at a given point is given by the moment load times y over I. So I is the moment of inertia. This is the geometric dependency of the loading I was talking about. So again, you don't need to know too much. Like, there's very standard formulas for computing the moment of inertia of standard parts or standard shapes, and you basically just plug it into the formula. And as a function of y, or your vertical position along that cross-section plane, you can predict the amount of stress on that plane. So again, really fundamental equation, but like, you can use it to predict things like loading on your upright or a whole bunch of different parts on the car. And for example, just to go back to that workflow, in terms of sanity check, like, if I'm designing a part and I have an idea of how much moment load I expect on the part, then I could relatively easily like come up with an approximation for that cross-sectional area, right? So if I need to determine how large I need to make this part or what material to make it, I can just really easily solve for the peak stress at the outside of the part, since when you bend it, all of the peak stresses happen on the bottom or the top. And based on that peak stress, then I can basically get a sanity check for, have I made my part large enough to react this load? If it's a tube supporting a bending moment, I can tell if that tube is large enough. Or I might realize, like, oh crap, my material is not strong enough, or I don't have enough space to do that. And I don't have to go through all the steps of setting up an FEA, failing the FEA, going to Kieran or someone else and going like, oh, my part failed, what do I do? Like, it's an initial gut check, and based on that, I know how to proceed with designing the part and not wasting my time on setting up FEA or something like that. So another super common form of loading is what we call, I guess, torsional shear. So as opposed to the moment load, in this case, I'm applying a torque that's, I guess, aligned with the cross section that I'm taking. So whereas on the previous example, I would be loading this bar again with the two ends like compressing against each other. In this case, I'm applying a torque like kind of in the plane of that bar. So this also results in a different behavior. And this is kind of where we go from what you would describe as normal stresses to shear stresses. So the kind of distinction is a little confusing at first. A normal stress is kind of like if I take a cross section of my object, that's the load perpendicular to that cross section. The shear loads, in contrast, are actually in the plane. So if I, again, were to take that cross section, the shear loads are kind of all aligned like where my finger is pointing. So these loads are in the plane of the cross section themselves. So this diagram here is just kind of showing that we have this plane of the rod right here, and these values of tau are what we refer to as a shear stress. So it's very similar to the normal stress. You basically just have a different direction of the load, and it's still a pressure at the end of the day. And you can actually relate the shear yield point to the normal yield point. And these are different per parts, but they're related based on the elastic modulus. So there's a conversion from normal stresses to, or normal strengths to shear strengths, which is a little more difficult to find if you're just like looking up a data sheet. But if you ever need help on that, just come and ask me and we can figure it out. So yeah, for the torsional shear, it's actually somewhat similar to the moment case. So if I apply a torque of T to a given part at a radius rho away from the center line of that part, the overall shear stress that I experience is still dependent on a moment of inertia. In this case, it's what you would call the polar moment of inertia. So a little different than the previous case. In this case, we're integrating over angles as opposed to like Cartesian coordinates to find that geometric property. But again, you typically just have tables like that you can look up the equations for. So in this case, you know, the rod is just pi, the diameter to the fourth over 32. So you just take that value, plug it in your equation, specify a torque, specify a radius that the torque is applied at, and then you get a shear stress out of it. So super simple. And again, the derivation is a little involved, but like fundamentally, you just need to recognize the behaviors of it, right? So the overall angular deflection is also dependent on this torsional load. So similar to the normal load case, the deflection is just proportional to the amount of load that you apply, right? It's just a slightly different way of computing, I guess, what kind of load it is and what plane the load is acting in. So again, there's just standard formulas for this, but what you should recognize about shear load cases is that the shear load is typically highest at these edges, or the further in radius you go out of the part, the higher your shear load. So if you remember back to the normal bending load case, it's somewhat similar where you get these peak stresses on the outside of the part. So it's no different here. The peak stresses are on the outside of the part, and typically you kind of identify those stresses first, and you kind of act or you check your part strength based on those peak stresses on the outside. The other unique thing that you'll notice is that a lot of parts that react extremely high loads in torsion, they'll typically be hollow in the middle. So you'll ask why. Like if you hollow out the middle of the part, you're just making it weaker, right? But it turns out that since all of your shear load is on the outside of the part, you can get a higher strength to weight ratio if you focus all of your material on the outside of the part. So if you gave me the decision to make a solid rod versus a rod that had a lot of material on the edges, like a tube, like typically if you're trying to react a very strong torque for as little weight as possible, you would prefer the one that has the mass concentrated on the outside as opposed to the middle. Because at the end of the day, I'm just failing on the outside of the part here, right? If I add more material in the middle of the part, I'm not taking advantage of that full yield strength. I'm only loading it to a fraction of it. So highly torsionally loaded parts you'll generally see are in more of a tube shape for that reason. So yeah, this section, I guess, is fundamentally pretty similar, or it's no different than the cases we've already looked at. It's just an example of how you might see this in practice. So something you'll hear extremely commonly is don't mount parts in single shear. So what does that mean? If I have a bolt, for example, here, and I'm supporting some kind of joint with it, so you'll see this all over the car, right? You have some kind of bolt, there's a loaded part that the bolt supports that's kind of butted against another part. You generally prefer to have the bolted member supported on both sides. So the reason for that is when I apply the load on this part, first of all, what I'm doing is I'm generating a shear on the surface. So the force is acting in plane of the cross section. So I'm generating not a torsional shear, but kind of like a vertical shear in this case. So you can imagine like the loads or the pressures distributed across his face pointing upwards. So that's the first part of the loading. But if you only support it on one side like this, you also get a slight amount of moment loading. So you generally want to isolate your parts to the loading case that is most optimal, right? If I have bolted connection, I don't want to be holding it like this and applying a moment to it as well. So if I support it on both sides and then I apply the load in the middle, it's generally going to be a lot stronger because you're only dealing with one type of loading mode. And that loading mode, I guess the shear in plane, is much stronger than if you were to solely support it via a bending mode. So as you're thinking about how you connect parts, how you design your parts, like try to recognize these patterns of loading. Ask yourself, like in this region of the part, am I dealing with shear loads? Am I dealing with bending loads? And then start asking yourself, how can I constrain this part differently so that like even if I'm supporting the same load, how do I change the loading within the part to make it more optimal? Again, like if you do this in FEA, you're just going to, you'd probably just end up upsizing this rod like over and over and over until it can support this bending load. But if you understand kind of the mechanism and form behind the loading going on in the part, then you don't have to go through that process. You can recognize much more efficient ways to load parts. And there's too many examples on the vehicle of like how to do this, but the most common one is that we have what are called like two force members in the suspension. So the constraints are specifically designed such that all of your control arms going to your wheels are only loaded in tension and compression. So that's like kind of a surprising thing at first. You have this extremely high moment load on your tire as you apply normal loads to it, yet everything that supports it on the car only supports it in, I guess, purely tensile and compressive loads. And again, that's just by being extremely smart about how you constrain the part. And if I'm able to do that, I can resist much higher loads than if I were loading my tubes and bending. So constraints are another super important aspect of part design that you kind of recognize once you go through these exercises of looking at the solids. And yeah, there's, I guess, equivalent considerations that you make for bearings or really any kind of interface between two parts. I won't go into too much detail, but again, the general gist of it is recognize the patterns of loading that go on in your parts and recognize the constraints that result in those patterns of loading and kind of try to design those out so that your part is loaded as optimally as possible. Another super common failure, I guess, is what I was alluding to, where if you just have some kind of supported member with a bolted joint, you can really easily just like compute how it'll fail based on the shear strength, right? The shear is just the load divided by the cross-sectional area here. So again, these joints, if I were to go and like catapult and like FEA it, that's like just too much. Like it's one equation and I can assess the strength of my joints and many other things just with this basic equation. Yeah, I'll probably skip this area. Yeah, this is just another effect from the bending. Like if I were to bend my phone, I have that kind of normal stress that we were talking about before, but there's also an effect where there's slight shear loads across the plane of the part as well. But yeah, I'll link the Shigley's book, and it kind of divides it up into these different sections of loading. So if you ever recognize a certain phenomenon is going on, you go and reference the book and just look up the formula. And it is typically still much more efficient for understanding the problem than doing an FEA. Something else you can do with these equations is you can predict the actual behavior of the deflections for certain cases. So something you'll see very commonly is beam bending diagrams. So these are basically describing the internal loads on a beam. You'll do this, I think, in, is it statics that they teach us on? Yeah. Statics, okay. Yeah, so I think most of the leads have probably been exposed to this at some point. But you can make these super nice diagrams that it turns out that all of these things, again, are interrelated. The amount of shear on a part is related to the moment that goes on in the part. And I guess you kind of have to go into the theory for this, but it's all related via derivatives of these different quantities. So you can get a lot of information just by using these very basic forms of equations for like a well-established system like a beam. Okay, so we've kind of talked about normal stresses, shear stresses. How does this actually work in 3D? We've only like kind of talked about like 2D cases, right? So this is more of a for fun thing. You probably won't ever be dealing with like calculations on the scale, but in general, any part has what we call like a differential element. So imagine if I were to zoom in super small on a single element within a part. You can actually describe the loads that go on in that single element via these normal loads and the shear loads. So as I was mentioning before, the normal loads are always in plane, right? Or sorry, perpendicular to the plane of loading. So these are all perpendicular to the faces, whereas all the shear loads are basically in plane on those faces. So you can predict the loading on a 3D level by using something called the Cauchy stress tensor. So that's basically like a really fancy way of describing the loading for like a particular point in a part. And when you do FEA, it's basically breaking up the part into these finite elements, as the name implies. And it's essentially computing that tensor based on a given constraint of your part. So this is like the general way that you describe loading at a given point. Again, like in practice, you usually never need to know this, but it's just kind of cool. You have a matrix that's 3 by 3, or rather a tensor, and there's 6 terms that you need, and you kind of fully describe the loading the part there. The thing that you do want to fundamentally understand is that how many of you are familiar with like linear algebra bases? Probably not that many. We got one. The cool thing is that you can actually describe any, you can describe the loading of a part with only 3 values, which you call the principal stresses. So there's a combination of normal loads and shear loads on a given element, but you can actually convert all of those shear loads by kind of rotating your reference frame. And if you rotate it in the right way, you only get 3 normal loads on 3 faces. So you'll sometimes hear this referred to as principal stresses, and it's a convenient way, I guess, of predicting the failure of the part based on just these like 3 numbers. And there's something called failure theories that you use. So based on the stresses at a given point, you can compute if the part fails or not. So we'll talk briefly about that. So yeah, these principal stresses, the idea is that if I have these combinations of normal loads and shear loads, if I rotate my frame of reference like this, there's a proof that you can do that basically says I can reduce all of these loads into like 2 loads in this case in plane, or 3 in general if you're in 3D. So this is useful because you can describe the loading based on only 3 parameters at a given point in the part. So this is what you would call the eigenvalues of the Cauchy stress tensor, which is a mouthful, but the eigenvalues basically mean that there's 3 values that describe the stresses at any given point. So shear stresses can be converted into equivalent normal stresses if you rotate your reference frame correctly. And this is kind of the formula for it. It's relatively simple, but you'll see these referenced in what we call failure theories. So you can use this principal stress relationship to predict certain types of failures. Yeah, this is all kind of extraneous. There's formulas to compute this. I won't go into too much detail. You probably recognize the, are you in solids right now? Okay, yeah, this is like more circle stuff. Yeah. So if you ever see a diagram like this, again, it'll probably take too much time to work through it right now. This is just converting shear stresses to equivalent normal stresses, and there's different ways to do that. But yeah, this is called the Mohr circle. Okay, so now we've kind of, I guess, covered how do we describe the loading on a part. Generally, how does the part respond to that kind of loading? So now's the next question. Like, if I know how the part is loaded, how do I actually predict if it fails? Like, up until now, we've only talked about the yield strength of the part. But like, when this goes on a 3D level and I kind of predict all these stresses, how do I actually predict if it fails? So this is something called a static failure theory. And the idea behind this is I have a description of my stresses for a given material. How do I describe if it fails? So it turns out the answer to this is really complicated. It's not just dependent on the stresses, it's also dependent on what kind of material you have. If you have a brittle material, the failure you'll expect is very different than if you have a ductile material. So there's no really one encompassing theory that kind of describes all of this. These are all kind of like approximations that we make to predict the failure based on empirical testing of these parts. So you'll hear all of these, I guess, different fancy names for failure theories. The super common ones are maximum shear, distortion energy, Coulomb-Moore theory. But the important thing you should recognize is that you'll never like really be applying these theories by hand much. Like if your part is sufficiently complex, you kind of rely on FEA at that point. But what you should realize is that FEA is really just like a manifestation of this failure theory, right? You give the FEA your constraints, you give it the geometry of your part, and you give it properties like stiffness, and it's loading the part and it's assigning a stress to each point within the part, that differential element that we were talking about. So based on that differential element, it then goes to a failure theory to say, does the part actually fail here or not? So the super common one that you'll see used in FEA, I believe is, I'm actually forgetting. I thought it was Coulomb-Moore, but I think I have it in a later slide. But yeah, it's just relying on some failure theory to say if the part is failing or not. And that's actually, sorry, it's von Mises. You'll see that in a lot of FEA plots where it refers to the von Mises strength. And that's kind of like a converted effective stress at that point that you can use to predict failure of the part. So you'll also notice that there's like reference to brittle and ductile materials here. And I guess the kind of intuitive way of understanding that is if you have a super brittle material, you'll typically fail in what's called crack propagation. Brittle failures happen extremely quickly because there's not much elasticity in the part. So if you put a part in tension that's brittle, it'll be much more likely to fail than the equivalent stress in compression, right? If I'm pulling the part away from itself, then it's basically going to initiate a crack at that point of stress and separate. Whereas if I'm pushing it together, like it's not going to develop the crack. You can't really develop cracks in compression. So just like that kind of intuitive difference between compression and tension isn't really something you get like by doing those hand calcs I was alluding to earlier. And that's where these failure theories kind of come into play. Let's see. So this is one example of a failure theory. And the idea behind maximum normal principal stress is you're taking those three principal stresses at the differential element, and you're essentially just saying, what is the highest normal stress there? And you're taking that and you're saying, if it passes a certain value, I fail. If it doesn't, then I don't fail. So it turns out that it's a relatively bad way of doing it. One of the reasons is like, it doesn't account for the differences in, I guess, compression and tension. And if you were to like plot this on a diagram, you'll see that your parts in general, I think this is a less conservative theory. So you'll get parts that fail when the theory predicts it doesn't. So yeah. A lot of times you'll see these kind of diagrams plotted for the failure theories. So these are two principal stresses. We're only looking at like a 2D element right now. And the, I guess, normal stress theory is you're basically setting bounds, this rectangular bound on these axes, right? So if your parts pass that axis, then if the failure theory is saying that, oh, these will fail. So the failure theory is essentially predicting where in this region the part is failing. And this theory turns out to be bad because it's not good for ductile materials. And this is because parts are generally much stronger in normal stress than shear stress. And if you only rely on the normal load, even though that's somewhat related to the shear stress, it doesn't consider that as a separate quantity. And it just lumps it into this principal stress. So yeah, not a great theory. There's a couple other theories, like there's the converse, like instead of considering the normal stresses, what if I consider the shear stresses? And you get a similar diagram here, except that it kind of cuts off the edges right here. So now I'm actually properly predicting failure of these points, whereas the previous one, it wasn't doing that. But it turns out that this one is actually still a little too conservative. There are some parts that it predicts to fail that don't actually fail. So in general, more conservative failure theories will cover a smaller area of this, right? If I predict a large area, then I'm going to get some parts that fail, like in this fourth quadrant right here. It predicts that these are safe, but they actually fail. So as I reduce the area of that permissible, I guess, failure region, then I get a more conservative failure theory. So all failure theories in general take the principal stresses and or the shear stresses and try to compute this general area of failure. And the one that FEA actually uses is called the distortion energy or von Mises strategy. So the idea is that, again, I alluded to this earlier, compressive forces in general, your part can react better and handle higher amounts of than stresses that tend to pull apart the part, right? So you have what's referred to as, I guess, strain energy. And again, I won't go into too much detail, but there's this formula you can apply to compute the von Mises stress. And based on this singular value, you can now predict failure of the part or not. And you get this, somewhat unique elliptical shape in the principal stress space. So it's a little, I guess it's less conservative than the shear stress case. So it tends to predict part failure pretty well. And this is, I guess, kind of the standard for most parts. Again, if you're dealing with like a super unique part that's extremely brittle, you might refer to a different failure theory. But in general, most metals that you work with that are relatively elastic, somewhat ductile, like steel, aluminum, are going to be really good for this theory. So FEA is going to be your, I guess, a pretty good approximation for most parts that you make on a car like that. So yeah, there's brittle failure theories as well, and you can see that the kind of form of the region that you encompass is really different. But at the end of the day, you're just defining some region where you predict non-failure versus failure. And people have already kind of validated this for you. So you essentially look up, I guess, which failure theory you should use in a given case. But most of the time, von Mises will work just fine. Okay, so for the end of this, I guess I just have a somewhat brief discussion on material selection. So most commonly on the car, you're going to be using some form of steel or aluminum, and in some cases, we use some polymers or plastics. So steels are really the most fundamental metal that you study in ME. So I guess what you should recognize is that not all steels are created equivalently, right? A given steel, depending on its heat treat or other properties, the alloys that they put in it can have vastly different yield strengths. The thing that kind of lumps together a given material is actually the Young's modulus. If you look at different steels, even though they have different yield strengths, they're still going to be relatively similar in stiffness. So even as they're doped with all of these different metals, like the primary constituent is still the steel on an atomic level. So that's why the stiffness remains pretty similar, even for the same type of material with different dopants or different heat treats. So why would we want to heat treat, or why would we want to, I guess, do something like, I don't know, strain harden a material? The reason is it's kind of a trade-off between ductility or toughness versus hardness in most materials. So if I have an interface that I guess is undergoing extremely high contact stresses, I might select a heat treat for steel that is extremely hard and is resistant to that kind of galling that I got on the surface, right? I want the hardness of the surface for many shafts is the primary consideration. However, if I have a different part that needs to, I guess, undergo a lot of shock loading, or you don't care as much about the hardness because you don't have as many contact stresses, in that case, you might prioritize toughness over the yield strength, right? So the general trade-off is that yield strength tends to go up as you make the part harder, but it's also more brittle and it tends to fail more suddenly. Whereas if you bring the yield strength down and the hardness down of the part, it's slightly more tough, but it has a lower yield strength. So material selection is really just about recognizing these different properties, recognizing your use case, and kind of trying to match those two. There's not like a magic heat treat and I guess doping for a given material that just works for everything. It's kind of tailor-made. You choose the heat treat, you choose the treatments based on what kind of situation you're dealing with. And these materials also have like other different properties fatigue-wise. I won't quite go into that this time around, but it's really just about recognizing these different properties of the material and matching it to your application. And yeah, I wish I could go over like, a step-by-step process of like how you choose the right material, but it's just so dependent on like the situation that you kind of learn by doing. Like you select a material, you go to the design review, and some more experienced members will point out like, hey, this part isn't hard enough in this region, or you might want to heat treat it. And you kind of learn from experience, and you learn to recognize like when you might want a certain type of material. And there's also like very, I guess, common alloys that you'll tend to choose. So most of the time, you don't need to be searching through like every alloy for material. You identify the common ones, like 1020 is super common for steel, or chromoly. So those are those standard ones you kind of learn to recognize again through building off the experience of other members. And once you kind of have that like internal bank of materials, like you kind of just think through it on a situation by situation basis. And obviously, for the most part, we tend to use steels and aluminum for highly loaded components on the car, because those yield strengths are just much higher than you're ever going to achieve with a polymer, right? So we typically reserve polymers for enclosures or extremely low loaded parts or enclosures in general. So again, there's like general materials that you use for certain applications. For the most part, steels and aluminum are more than enough for most of what you do in the car. Okay, so yeah, this is a point in the presentation that goes into failure theories for fatigue, but I think that's, that probably warrants another section. So that's pretty much everything I wanted to cover. To close out, I'll go back to that original diagram. So as you're designing the part, let's see. Yeah, so as you're designing the part, it's kind of this flow chart of assessing the very, I can send out the PowerPoint too, so you don't have to screenshot every slide, but it's all about, I guess, using your intuition to recognize certain patterns of loading in the part based on your fundamental understanding of solids. And if it's sufficiently complex, only then you go to rely on FEA. And even once you do the FEA, you're kind of internally validating like whether your results are plausible or not by checking them against your understanding of these basic types of loading. And then after that kind of goes into the materials part of the selection. So you're selecting a material, kind of checking whether via hand calcs or FEA if it's viable, and you check the different heat treatments and everything after once you've kind of gone through that process. So yeah, I'll send out the presentation. Does anyone have any questions before we close out? Very intentional. Okay, so I guess just quick note on that. Carbon fiber falls in a different category of material. That's what you refer to as, I guess, like composite, as a lot of people know. The most important thing is that all of the materials I talked about today are what we call isotropic. They have the same, I guess, behavior regardless of the direction that you load it, right? As you go into materials like composites, it becomes a lot more complicated since you have, two or more materials, a matrix and some kind of like a binding agent. So like, for example, you might have carbon fibers and an epoxy in a standard layup. So it doesn't behave similarly in all directions. So one, it's like super hard to characterize. And two, like any layup that we do in-house is going to be a lot more inconsistent than like a very precisely alloyed material of like metal that we get out. So there are fundamental differences like in the behavior of these two parts, but carbon fiber is much more difficult to analyze specifically because of the anisotropy. Like it behaves differently in different directions, and the material properties are also difficult to predict. So there's a much higher bar for analysis, I'd say, for those kinds of parts, which is typically why like we don't encourage new members to start with those, like start with kind of the predictable parts. And once you understand that and can characterize them, work your way up to the more advanced stuff. So yeah. I sent Kevin all of his homework last night and then he didn't show up. I got conned.